All right, welcome to the show, everybody. Thanks for coming on. This is actually going to be, I think, one of my favorite talks that we've had in a really, really long time. If anybody has been following the show or listening to the questions that I ask, they're often around data frames and how to manipulate data and how to work with data in ways that really pandas can't handle. We've had Vakes on the show once, if not twice already. This is one of my favorite topics, and we have a new contender for the king of the data frame world. And so I'm extremely excited to bring him on. We have Jay. Jay's coming on, and Jay is going to talk to us about data frames and Daft, his new project. And he's going to talk to us all about kind of the assumptions we've been making about data frames and how those assumptions might be wrong or limited and how we can kind of break out of them. So Jay, thanks so much for coming on the show. I'm very, very excited to hear you talk.
Yeah, thanks for having me.
Awesome. So I'm going to let you jump right into it. And then at the end, we'll come back with questions from the audience and from me. But yeah, I'm going to let you jump right in. Oh, and we have Demetrius, of course. He was so excited.
Wait, I got to say one thing. I'm going to crash the party real fast because we've got too many good things happening in the community for me not to say it. So I just got to put this little ad break in here and mention that there's a whole LLM in production conference coming up pretty soon. And we've also got in-person events happening all over the place. So we're doing a hackathon in San Francisco. In case you are in San Francisco, we're doing a whole LLM stack hackathon that you're going to be judged on your stack and your quality of it. And there's all kinds of good prizes. And we're also doing it in Berlin. So we're doing a what you can build on top of LLMs and vector databases in Berlin on June 16th. And the LLMs stack one in San Francisco is on June 3rd. I'll drop all the links to all this stuff in the chat right now for everybody to see. And Jay, don't let me take any of your shine. I'm going to hand it back over to you and get off the stage. I just wanted to mention that for everyone.
Yeah, and if anybody, I'm just going to drop it here so everybody knows there are some very, very funny t-shirts and very cool swag that Demetrius is working on for the community to check out. But you got to go to the conference to see those things. So yeah, Jay, take it away.
Awesome. Yeah. So hello from sunny San Francisco. Well, it's not that sunny today, but I'm ready for my LLM shirts for sure. Hope to be in person for that event. Yeah, so hi everyone, my name is Jay Chia, and today I'm going to be talking to you about data frames, and why a good data frame library might be all you need to start with in MLOps, and also tell you a little bit about Daft, which is the project that my team and I have been working on. We are the Python distributed data frame for what we are calling complex data. Some people call that unstructured data, like images, NumPy arrays, point clouds, audio, all these data types that you don't traditionally expect to fit into a data frame and traditionally expect to be able to manipulate in a data frame. Daft does really, really well. So we'll go a little bit more into Daft later on. But the title of the talk today is, data frames are all you need, how to put MLOps on easy mode. Stop building all these crazy infrastructure to work with your data, just use a data frame. And so maybe first a little bit about myself. So I am a co-founder at a company called Eventual. Before this, I was a software lead at Freenome, which we were working with genomic data, all kinds of weird data formats for like proteomics, genomics, autoantibodies, and weird biology data. Lots of PDFs as well for like, doctor reports and all that. And then I worked at Lyft L5 on autonomous driving. So again, a lot of multimodal data revolving around LiDAR, point clouds, images, radar, weird data types, and found myself building a lot of the same distributed data systems for machine learning type workloads, machine learning type of data, converting these multimodal data formats into features and into things that machines can understand. And along the way, I figured out actually all you really need is a really good data frame library. And so me and my co-founder, we came out and we started writing Daft. It's a pretty young project, just a couple of months old right now. And it's a data frame library and available. You can check us out at daft.io. And yeah, we love data frames. So let's jump right into it. To make sure everybody is kind of on the same page, we'll be going through data frames. What is a data frame? why you should really care about data frames, and why data frames as a abstraction and concept may actually be way more useful than you think. So first of all, what is a data frame, right? Most people will probably know pandas, and a lot of people I think got their introduction to Python through pandas. But I would say pandas is a data frame library, but personally I don't do mine, and really think of data frames as this higher level idea, right? It's an idea of a programming data structure. So it's something you can manipulate in Python. It's an object you can pass around in Python. This data structure is a table, right? Data frames have rows and then they have columns, and every column has a name and a data type. And so we're going to be using Daft as kind of a running example throughout the presentation. This is an example of a Daft little data frame that I printed in our console. And so you can see that there are rows, right? And every row has 4 columns, label, numbers, correct, wrong. And then every column has these data types, often abbreviated as D type in a lot of libraries. So when you have these D types applied to the columns, you can always be sure that every element in the column is of the same type. And so in this case, there are these integers. This numbers is an unsigned integer. And having this really rich type system helps data frames give you a lot of functionality, right? And also helps data frames ensure a lot of things about these tables that you can then assume as you do your work. So really, TLDR, think of a data frame as a table that you can manipulate in your program. There are a ton of data frame libraries out there, especially in Python. So we have pandas, obviously, that we all know and love. Daft, I have to plug it. Me and my team have been working on it, and there are a bunch of other data frame libraries out there as well, like PySpark, which is a wrapper on top of Spark that provides you with a data frame API on top of Spark. Dask also has a similar wrapper, which provides a data frame API on top of Dask. There's a library called Polars. People may have heard of Vix, Nodin. Really, they're all these different data frame libraries. I would say they differ in terms of maturity and differ in a whole bunch of other axes as well. Some of the main ones I have listed out here. So data frames can be lazy or they can be eager. If you're familiar with pandas, that's an eager data frame, right? Every time you run a command, pandas immediately runs it and immediately shows you the result. A lot of other data frame libraries are instead lazy. So Daft, for example, is lazy. When you run something, we don't immediately run it. We kind of queue it up in a little query plan. And then when you're ready to run it, you say like, hey, Daft, run the plan I just told you to run. And Daft will do a lot of intelligent optimization to, for example, like, hey, like you don't actually need this column. I won't even read it, right, from storage. And so that's the advantage of a lazy data frame, where you can be a lot more intelligent about the way you're working with your data and let the engine kind of handle that for you. Data frames differ a lot in terms of the types of data that they support. A lot of data frames may not even support Python objects, for example. You may not be able to put Python objects in your column. And then, data frames often will support things from numbers to strings to dates, but you won't see data frames out there. I believe Daft is probably one of the only ones that will support things like images, embeddings, tensors. We're also looking at supporting, things like audio, PDFs, etc. And so the types of data you can put in a data frame are often very different between libraries. The third point I want to make is about distributed computing. Most data frame libraries are really good when you have it on a single machine on your laptop, which is great, I think, for most use cases, 80% of use cases where all the data fits on your machine. But when you have data that's maybe a bit more unstructured and a bit more complex, like images and large NumPy arrays, then that's where you may consider, I do need kind of a cluster of machines maybe, and my data frame needs to be able to have the same table abstraction, right, locally from my programming environment, but this table actually needs to run on 100 machines, right, because I have that much more data. And then, of course, there's the speed aspect of it. Data frames can be faster or slower, and they have very different APIs. And so all of that to say, data frames can be very different, but the way that they're similar, right, the table stakes, pardon the pun, is that data frames have to be really, really good at reading and writing data. That's because data frames don't have a storage backend. So that they're not databases, right? They don't have built-in storage. You have to connect them to your own storage, and so they have to be then really good at reading and writing data, especially tabular formats like CSV, Parquet, JSON lines, etc. And so the second thing they have to be really, really good at is data processing, because oftentimes what you're trying to do is you want to go from column A to column B and apply some transformation in between. That transformation may be a Python function. That transformation may be a simple +1, right? Add 1 to a column. And Dataframes need to be really, really good and really, really efficient at that. Other things in the realm of data processing is joins. Joining two tables together by the same key is a key operation when you're working with tables. And so Dataframes have to be very, very efficient at allowing to do those joins to enrich your data with some other table. The third thing that's table stakes for Dataframes is data analytics, right? The whole reason you're using a table in the first place is you want to be able to do these operations across rows. You want to be able to sort, right? You want to be able to count the number of occurrences of certain things in these rows. You want to be able to sum across a row. And additionally, you want to be able to group by a certain key and do that for rows that always have that key, right? And so these are kind of what really define the Dataframe API and things that all Dataframe libraries will support. And they support them with varying levels of expressiveness depending on the Dataframe library you're using. And you should make sure that the Dataframe library you're using is able to support all the expressions and things that you want to run on your data. Okay, so that was the little plug about Dataframes to make sure everybody's on the same page. So now you may be asking, hey, Jay, I do ML, like this Dataframe thing is about data, like, so why should I care? I'm sure people have seen this before. It's the sprawling tooling landscape of MLOps, right? There's so much tooling all around. It's really hard to wrap your mind around, like, oh, what do I actually need versus what's like nice to have, or like probably I need at a later point, right? When my team is at a certain level of maturity, or my stack is at a certain level of scale, and I need a certain level of, say, reproducibility. But I'm a simple guy. I understand things in 2s and 3s. So I have like 3 main things I think about when I think about MLOps, and 3 main points for these main functions. And so MLOps to me is really about, you have your data systems, right? That's where you think about like your feature stores and your batch ETLs and all that, the data systems realm of things. And then you have training, which is where you do model training. And then you have productionization, right? Which is very different depending on the type of application you're building. But really, these are kind of the 3 main big pillars in MLOps for me. And to dive a little bit deeper on the data side of things, very simple. All you're trying to do is you're trying to store and retrieve data, right? You want a way of like doing that. You have your different data types, and you want to be able to store and retrieve it. You want to be able to explore it, right? Really understand your data, dig into it, run all these statistics, run all these group bys and aggregations to really understand it. And then you want to process it, right? You want to be able to run models on your data. You want to be able to clean up your data, right? All the rows that have nulls in them, you want to, like impute them and put data in. And these are all operations that you want to do in the data realm to produce these really good data sets for downstream consumption. And so once you're done with the data realm, oftentimes people think about training. This may or may not change in the coming few years with LLMs coming into the picture. But traditionally, I think this has been a pretty strong pillar in MLOps, where functions here are also very simple. First, get the data, right? Number 2, train your model. And number 3, figure out how well that model did, right? Evaluate the model. Also, it's super simple. And you're usually getting the data that you've previously pre-processed in the data functionality of your MLOps stack. And then the third thing is now you have your model. Now let's start using it, right? Put it into production. Again, super simple. It's usually some function of these three things, which is number 1, get the model somehow. Number 2, use that model, right? Run it. And then number 3, figure out how well that model did. Check the results of that model by figuring out how to, checking against some new data that you're getting in reality in production. And my goal here is actually, now that we have this layout, let's think about where data frames and Daft can fit into the picture, right? So on the data side of things, very obviously a data frame is super useful. So you can use Daft to read and write all kinds of data from storage. So you can read and write CSVs and Parquet. And in the future, you'll probably also be able to read and write things like from Postgres and from all your different like data sources. Exploring data, a data frame like Daft is also super useful because then you can do all these aggregations, statistics to really, really understand your data, right? Understand data skews, understand where you might need to collect more data, where you might need to balance out your data, or where your data is just really bad and you might want to just get rid of it and make sure to mask it out. And then thirdly, data frames are also should be really good at processing data. And so that's a key part of Daft as well. Like, can I run a model through my data frame, right? Can I run these really heavy computations? Can I call an API through a data frame? These are all things that your data frame should be able to support, and Daft does. On the training side of things, once you finish with your data, which is, a lot of people say is 80% of the work in machine learning ops, what you do is in training, actually, a data frame can be really, really good at getting the data for training, right? And if you're doing any sort of GPU training, this becomes incredibly important because the main bottleneck for a lot of GPU training is data ingest. You need to saturate your GPUs with enough data to make sure that you're getting your money's worth. Otherwise, you're going to get like 5% GPU utilization and you're just wasting your money. So a good data frame library should be able to support this kind of high throughput ingestion into your training pipelines. And then once you've trained your model and you're trying to evaluate it, it's also a pretty natural fit for a data frame, right? You're going to use the data frame to run your model and then do a bunch of aggregations to understand, hey, how did my model do, say, across geography? How did my model do across, job occupation, right? These are all things that you may want to explore once you've, or actually during training, as you're running through the different epochs of training to understand how your model is progressing along those lines. And then lastly, in production, if you're doing batch workflows like most of us, you would pretty much just want to use the model that you've just produced and run that in a batch fashion, which is, again, perfect fit for a data frame. And then checking the results once you've run that, perfect fit for the data frame again, because you would usually be joining your model. Once you run the model, you have this data set, and now you want to just join it, right, with like new data that are coming in that you can then use to verify, hey, how well did my model actually do, right? For example, if your model is, predicting click-through rates, right, and you have the model predictions, you may want to join that with a new table that says, how many of these users actually clicked these links in the following 7 days, right? And these are all data frame operations that are super, super native, and a good data frame library should allow you to do all that very seamlessly. And so all that's to say that, it's my opinion that actually so much of the MLOps workflow can be done with data frames. But here's the kicker, right? People often ask, hey, what about all my unstructured data, right? I have all these weird file formats that I can't put into my SQL tables. And traditionally, data frames have been kind of constrained to that working model where it's very SQL-like. The types of data you can work with in the data frame are like numbers and like dates and strings. Doesn't really go beyond that. And so once you have all these, people call them unstructured data. I think that's a misnomer. They should be called more complex data because all data has structure. But if you have this type of data, this multimodal data modality like images, JPEGs, PDF files, protobuf files that you dumped out from your systems, JSON files, right, XML, HTML, the list goes on and on and on. The question there is, what do I do with all that, right? I can't put them into my data frame because my data frame doesn't really do a good job of helping me process this type of data, right? Oftentimes you may want to provision custom hardware even to process the images. So I've done this, I've been guilty of this as well. Often people will have kind of this SQL-based structured query engine, which could be a data frame, right? Or it could be something like Snowflake or your data warehouse sitting on top. You do all of your table-based operations there, and then you have maybe like URL pointers out to these files that are just sitting in S3, right? Where you then do this unstructured batch processing where like you fire off a large job, hey, run these million images and then produce results and then write back into your table. And that gets super unwieldy and super hard to deal with, because then you have all these different pointers and it's hard to manage two systems, and really hard to resolve the disparity between these two systems. Our claim is they should all be able to fit into a data frame. So again, this is a screenshot from Daft, where we have, in one column, the URL. We were very easily able to go from the URL to an image, and then from the image to a thumbnail of that image, right? And everything fits in a data frame. And from the Daft point of view, there's no real reason why this type of data can't fit in a data frame. It's just, I think people have gotten used to the idea that, data frames are good for like dates and strings and numbers, but really they should be good at containing any type of data. And so Daft is able to support all that by allowing you to, first of all, put in Python objects. And second of all, we're also working on a lot of native types for things like images, common data types like images, protobufs, PDF files, HTML files, things of that nature. So I think the bare bones machine learning stack kind of looks like that, right? You have what's, your quote unquote feature store, where you can define both the storage and the compute on top of your data. And that usually looks like some combination of storage plus a query engine, right? And really, the choice of this depends a lot on your use case. If it's purely tabular, SQL might actually be a really good option here. You can, use something like Snowflake, where it has inbuilt storage and an inbuilt query engine that's SQL based on top of that. I would argue that if you are dealing with anything more than that, and you need kind of a better solution that interfaces well with your downstream pipelines like Python, then you might consider something more like Daft. But at the end of the day, for like just starting off with machine learning, and for I think 80% of use cases, this is probably true, where all you need is a really good query engine on top of a storage, and then you have your machines running Python and all of the Python ecosystem for ML, right? Like PyTorch and NumPy and sklearn and all of that. And so where data frames fit in is it fits in really nicely into this query engine portion that allows you to have this really good abstraction on top of your data. Okay, so I'm going to now jump into a demo. I promised a lot about Daft and what it can do. So let's actually take a look at some of the things that Daft can do. And so today I have a little demo prepared on the Cocoa dataset. Some of you may or may not be familiar with this dataset. It's basically one of the canonical major image datasets. And so it looks like this, where the dataset comprises of images. Each image has bounding boxes, right? So they don't show it here, but a lot of these images should have boxes around these objects. So this one should have a box around this motorcycle. This one should have boxes around the dogs. And also they provide segmentation masks, which we aren't going to be using in this tutorial, but that looks a bit more like this. So instead of just regular boxes, you get actually the polygons that surround each object. But this is just to give you a good idea of what the data set looks like in general. And now we're going to try to use Daft for everything we talked about, from reading and writing the data to data exploration, down all the way to data processing, and then make that little jump into training, right? And then do model evaluation, which can be done during training or in production when you're running your model in batch. So let's jump right into it. First of all, to install Daft, what you can do is you would just do a pip install get Daft. We are get Daft, so make sure to install the right one. And once you're done with that, I have pre-installed Daft here. All you got to do is do an import Daft, right? I am going to run Daft on a Ray cluster for the purposes of this demo. This is running on a local Ray cluster, so on my local machine, because there are some features that I wanted to show y'all that's only available on this backend. But by default, Daft actually runs on a super lightweight Python multi-threading backend, and you can run Daft completely on your laptop without any Ray or any of those dependencies. So now that we have Daft up and running, we're going to go ahead and start reading some data, right? So I'm going to have Daft read some Parquet files that are in S3. I have them stored in these S3 buckets. And now that we have these data frames, we have one for the images, one for the annotations, and one for the categories. Let's take a look at what Daft pulled in. So I'm going to print the annotations data frame. It's going to show you a whole bunch of columns, right? these columns actually have pretty complex types because of the nature of this data set. So there's a bounding box, which is actually a list of coordinates. It's a list of 4 items always. And then there's, the segmentation masks, which we talked about, which is the little polygons around the objects, and a bunch of other things that it's kind of hard to tell, right? And the reason why Daft doesn't show you this data is because all it's done so far is parse the data to understand what columns there are in the data. And until you tell Daft to execute, it doesn't execute, right? It doesn't actually pull the data down until you tell it. And this is because Daft is lazy, like we talked about earlier. And so if you want Daft to actually pull down the data, tell it what to do, right? Hey, Daft, show me, in this case, default of 8 rows. So when you tell it, hey, Daft, show me the rows, it's going to actually go out and pull the rows down. And now you can see that data, right? And Daft is going to tell you, yeah, I'm showing you the first 8 rows of however many rows there are. I don't actually know because I only looked at 8 rows. And now we can see the data itself. There's some sort of image ID, which tells you which image this row is from. Then there's a box, right, of the object. And there's a category ID, which tells you what type of object that is. And so, yeah, now we have our very first Daft data frame. Let's do a little bit of data exploration, right? So now we're kind of a little bit past the loading of data. Let's do a bit of data exploration, which is, very simple things that you can do in pretty much any data frame library. We have this categories data frame that sits alongside this. I want to now see for these IDs, what do these actually mean, right? The numbers don't mean anything to me. But if I were able to join that data frame with the categories data frame, which has the name of each ID, right? I can do a dot join on the categories data frame, right? Join them on the IDs. Now I'm going to group by this name and then count how many instances of the names occurred in the data set. And this gives us a really good idea of what our data set looks like, because it looks like there's 11,000 instances of people in the data set, and that vastly outweighs any of the other classes, right? Like cars and chairs and books and all that. But yeah, doing this sort of exploration is part and parcel of having a really good data frame library to work off of. And Daft allows you to do that, just like most other data frame libraries out there. So I'm going to go ahead and run a .collect, which will pull all of the data into distributed memory, right? So we're pulling all the Parquet files in now. And it's pretty small, actually. It's 36,000 rows. There aren't any images in these Parquet files. It's all just IDs, right? So it's pretty cheap still. Okay, now that was all kind of like table stakes. Like every data frame library should be able to do this. Otherwise, it would be a pretty crappy library. Let's start using Daft now for some of the things I promised, which is like Daft is really good at processing this type of complex data types, right? So first thing I'm going to do is I'm going to join this data frame with another data frame, which has the actual URLs of the images. And so once you do that, this is what that then looks like. Our new data frame after doing the joining, right? Now I cleaned the data a little bit by saying I only want certain columns, right? After doing the join, I'm only interested in the, first of all, the object ID, right? The URL to the image that the object came from, the box within the image where the object is located, and then the category of that object, right? And now we have this little data set that's a lot cleaner, a lot easier to understand. It's just one object per row and the image that it came from. Great. Let's go one step further, right? And we can start actually pulling down data from these URLs and visualizing them on our Jupyter Notebook. So first thing I'm going to do actually is this little call to divide our data frame into 64 partitions so that Daft can then work on them in parallel. And now to go from these URLs to data is super simple in Daft. We expose a lot of these very powerful expressions. And so one of our most popular expressions actually is this .url.download expression, right? So all this is saying, hey, create a new column. Let's call image bytes. And the way you create this column is you download from this URL column, Coco URL, which was this column right here. Download data from that column, right? Hey, Daft, do a .url.download and then create this new column of image bytes. And so if we look at the new data frame after running this operation, Daft will tell us, hey, your new data frame looks like this. There's this URL column, which is a UTF-8 string. column, but now you have this new column, right, which is this image bytes, which is a binary column that we've downloaded all the data from. So now we're like, okay, this looks good. Daft, go ahead and run that, right? And when we do run it, we'll see that, yeah, Daft indeed pulls down all the bytes for each JPEG image, right? So basically all it does is it does this really efficiently, goes to each of these URLs, pulls down the image for you in, what was that, like 3 lines of code. Now going from the bytes to images, we'll use some of Daft's Python functionality, right? So Daft allows you to run Python functions in your data frame really easily. So I'm going to define a function here, which will take the bytes and convert them into a PIL image. PIL is a very common image processing library in Python. And to run this function on my column, all I have to say is, daft.apply to the image bytes column, apply this Python function, right? And you have to tell Daft what the return type is. So Daft, the return type is going to be another Python object, right? Which is the PIL image. So we'll run that. Fantastic. Now we have a new column of all the images. Looks like they are actually repeat images, right? All coming from the same URL, because these are all objects in this very, very busy image right here, which is a ton of objects. And now we can go ahead and define another function to have Daft crop these images based on the bounding boxes of the object, right? Again, super simple. I define a Python function that takes as input actually these 2 Daft series objects, and I can iterate over the series, which is we can think of them as like in-memory representations of the columns, iterate over them, and for each image, run the crop of the bounding box, right? And then I'll tell it again, hey, this function, returns a new column of Python types. And the way that you use this function in Daft is super slick. Just run this function that we've defined and decorated with the Daft UDF little decorator. And you can then run this function as if you're running them normally on just the columns, right? So you'll say, hey, Daft, create a new column called cropped image, run the cropped images function that we just defined, run it over these 2. Run my Python function for me. And yeah, looks like it did exactly what we told it to do. It ran crops. I also put in a little pizzazz in here, a little bit of resizing to do it, resize all the images to 224 by 224. And so now we have this new column, which are the cropped images. And we can start to see that, yeah, this one's like a bottle of wine or something. This one's probably the table. This one's a person, right, the chef. And so Daft makes it super easy. In just a few lines of code, we've gone from URLs down to bytes, down to image, down to cropped image. And lastly, what we want to do is go from cropped image to something that we can feed into training, right, which will be NumPy array. And again, super simple. I defined a simple function here to do this for you, which will convert these images to NumPy array. And so now, yeah, this is your final data frame where you've gone from these images all the way down to NumPy arrays. And so I think the astute observer here, if you're familiar with DAGs, would observe, hey, isn't this just a DAG, right? Like your columns are the results of previous columns. This is a very linear DAG, right? This column resulted from this column resulted from this column, etc. It's just a linear DAG. And yes, data frames are actually DAGs. And so, a lot of things that you may be using a DAG like workflow engine for, in order to do all these like crazy like jobs, you could actually just use a data frame if your data frame library is good, like Daft is for processing this type of data. And so now that we have this, right, this was kind of a demonstration of the data processing portion of Daft. We're gonna go ahead and start showing you how you can feed this into training. And so right now, Daft has integrations with Ray. We are working on just directly PyTorch integrations, but the way that you could feed it into training is first you create a Ray dataset. And now that you have this dataset, you can actually call, I believe it's iter torch batches, which will give you an iterator, batches equals to this. And then now when you pull data from this iterator, it's going to give you just like the PyTorch tensors that you need for training, right? So here are all the PyTorch tensors, and these are all already nicely batched up for you. And so what we've done is we've gone from this data frame we just tell Daft, hey, I just want the NumPy array column and I want the category ID column. Give them different names, right? Call the NumPy array column image, call the category ID column the label. And then now that we have that, and we can start just very easily start pulling down data from our data frame like that to feed into training. The fact that also we support Ray means that we support distributed training. And so if you're using any of Ray's distributed training utilities, then that fits in really well with that. And we're working on PyTorch specific integrations as well. And so that's kind of the training story. Once you have your model, right, you're like, okay, I have my model now. I need to run my model on a lot of data, right? Maybe you're in the middle of the training step and you're like, okay, here's Epoch Zero's model, right? Can you run this Epoch Zero model on like a test set? So what you can do is you can actually farm that out as a Daft data frame, right? Run that separately and then continue with the training even, which is pretty cool. And the way you can do that is we'll make use of the UDFs that we saw from before to define a new UDF that's a special UDF. This one's a class instead of a function. And what that allows you to do is in classes in Python, you can define how a class initializes itself. And we make use of this initialization to tell Daft that this should only be run once every time you initialize this class. And what we will do here is we'll actually download a pre-trained ResNet 18 model, right, and store that in self.model. And then now every time this class runs on new columns of data, you don't have to reinitialize the model. All you have to do then is we'll hit this call function. Classes in Python can actually be functions as well, and this is how you make them a function. Every time we call your custom UDF, which stands for, I guess I should have said this earlier, UDF stands for user-defined function. And so we have a class-based UDF, and now we're calling it on these images which are coming in. And every time we see this image column come in, we'll do a bunch of transformations to reshape them into the shape that our model expects. And we'll just run the model, right? We'll call this a self.model and run it on the images. So pretty simple. This is a pretty simple UDF that takes in just one column of the images and runs the model on the images and returns the labels of each object image. And the way that we use this UDF, also pretty simple. We're going to run it on our previously curated joined data frame, right? To remind you all, this is what the joined data frame looks like. It has these columns and it has this NumPy array column, right? That we want to then run our UDF on. We want to essentially use our model to predict this image. What is the category of the image using this pre-trained model? And so the way we do that is we create a new column, right, called predictions. We do create a join DF with a new column called predictions. We run the UDF on our NumPy array column, right? Just run the UDF as if you're running a function. Run the ResNet 18 UDF on this join data frame NumPy array column, and then we run we just want to select 3 columns, right? Just the columns we care about. Then let's show that. And in a few seconds here, we should be able to see that, yeah, we ran the model on these images, and now we have the predictions, which I've mapped back to the name instead of like a number. And it's fairly bad because this model was actually trained on a very different data set with probably different classes as well. But this one looks like an oil filter to the model. This one looks like a hammer, which is not a hammer. This one, for some reason, thinks it's a prison. Some torch, sure, that's reasonable. Cradle, reasonable, right? But all that's to say that it's super easy to run your models in Daft, and Daft makes it really easy to do that. One additional plug I wanted to put in. So I don't have GPUs on this machine, but if you wanted Daft to run your UDF with a GPU, all you have to do is add in this little resource request flag and tell Daft, hey, this step, this step that I'm running here, creating this new column, it's going to need a single GPU, right? And then Daft will make sure that when your UDF runs, it provisions exactly one GPU that your UDF can then utilize. And so that's how you can potentially speed up a lot of this workflows if you have GPU availability. So that's really cool. Everything was kind of running on my laptop on a small subset of data. But we can also go ahead and just take a look at how we can use Daft to, run on much more data using distributed computing, right? So I have a cluster running with Ray already. I'm going to connect to right now. This is just if you've ever used Ray, this is just a way of like initializing Ray and connecting to the cluster. And now Ray is going to tell me that, hey, you have 64 CPUs now, right? You connect to the cluster, and these are all the nodes. And the idea here is that you don't really have to change any of your code. You just have to connect to the Ray cluster, and then the rest of the code is actually exactly the same. Right? We can read the data just as we did before as part K. Show the data. I'm going to run through this really, really quickly. Go all the way down, right? We can then go all the way down to the NumPy arrays where we created these NumPy arrays. And then, so now the code is exactly the same, but all this computation is now happening on the cluster, which means that we can, instead of just running on the first 8 rows like we've been doing, we can actually have Daft run on everything, right? Because we have way more compute now. And so given that this is the end result that we want, looked at the first 8 rows, we're like, okay, Daft, run on everything now, which is about 40,000 rows, I believe. So we can do .collect to tell Daft to run on everything, and we can do time this. I believe this takes about a minute for about 40,000 rows of all images, which is pretty impressive, given that it's quite a lot of data. So yeah, and then when you're ready, you can then use Daft to also scale up. Oops, we have an error here. Not sure what happened, but when you're ready, you can actually use Daft to then scale up on GPUs as well in Ray. But yeah, I'll leave that for a further demo. There are a lot of other resources you can use to learn Daft by going to getdaft.io, and we have a bunch of documentation that you can take a look at. But I'm going to hop back into our little regular programming. And so, yeah, I wanted to talk a little bit about why Daft is uniquely suited for machine learning, right? Well, first of all, as we've seen, it's very Python native. So you have this first class kind of like REPL experience in your notebook. The second thing is that it's built for distributed computing, right? So if you have a ton of multimodal data, like images and all of that, you can use Daft to scale up over a array cluster to work with that data. Then, Daft is also really, really fast. We're actually pretty competitive with a lot of the faster than Pandas libraries on a single machine already. But if you needed to go distributed, we're also very competitive with Spark. I believe we're beating Spark by quite a bit in a lot of the benchmarks as well. And so this is important because the faster you can iterate on your data, the faster you can turn out models, and the better your application is going to be. The next thing is that Daft works really well with complex types. Right now, we do support only Python objects. We just added an embedding type as well, which is basically a fixed size numerical list that has some custom things you can run on it. We have URLs, as you've seen, which makes it really easy to download data from URLs, manipulate URLs. And coming soon, we have in the works, actually a PR is out probably today for image types. And so all that cropping that you had to do in Python, right, you no longer have to do that. You just call something like .image.crop or .image.toEmbedding, and Daft kind of handles everything for you. Then more types like audio and PDFs are on their way as well. And the last thing is that we built Daft to work really well with S3, which is really like the de facto solution right now. Well, if you're on a different cloud, right, if you're on AWS, it's going to be AWS S3. But if you're on Azure, it's going to be Azure Blob Store. If you're on GCP, it's going to be GCS. But the idea is that like the Dataframe needs to work really well with cloud storage for all of these modern workloads. And so I'm making the argument here that, perhaps this should be your bare bones machine learning stack where you have Daft plus S3 as kind of like your feature storage. And then you just have a bunch of machines running Python. And that's really all you need to get started, right? This allows you to do a whole bunch of stuff for data processing, for training, for, running your models at scale on large amounts of data. And yeah, you can find us at getdaft.io. This is the website. We have pretty comprehensive documentation. We also have a little Learn Daft section with a user guide, a quick start where you can view all of the or most of the important functionality in Daft. The Learn Daft section has a user guide, which is a more in-depth dive into each portion of Daft, and also a bunch of tutorials, right, where you can take a look at how you can use Daft in various contexts. And I guess a little sneak peek behind the scenes of what we're working on. We're working on way more Daft types, like I mentioned. So you're going to have image types. You can do like crops on images. We're working also on a lot of NLP use cases for, running, say, open source LLMs, or you can say like, create an embedding for my text. And then we can, behind the scenes, run really optimized Rust code to make that work for you. And we're also working on a lot more integrations, such as the PyTorch data loader, reading from more data sources. If you have a data source that we don't cover and you want to use it, come to us. We'd love to hear from you. More expressive queries, so you want more functionality in Daft, more kernels, right? And we're also potentially thinking about SQL interface if people are interested. Streaming and serving, right? How do we, instead of having Daft just be this one batch processing engine, how can we have Daft express a continuous computation so that every time new data comes in, new data gets spat out on the other end? And yeah, so if you have a use case that we don't already cover, come chat with us. We'd love to collaborate and work together on building those use cases out. And yeah, that's all I had for today. Would be open to any questions.
That was awesome. Thanks, Jay. That was really, really cool demonstration. There's a lot of awesome stuff. The first thing that somebody asked about was, can you give access to that notebook? I saw that it wasn't in the examples in your repo.
It's not, because I was just working on that last night because it's been a pretty busy week, so I was hammering it out. But I can make that available right after the meetup. Yeah, we'll put it into the examples repo.
Awesome. That was super cool. Yeah, the idea of streaming to me is very cool. Is the way that you're thinking about that, for example, that you would allow, for example, like a sink that you can just start sending data to, and it would ship to that location and it would process it and just ship out to the other end?
Exactly. I mean, right now in Daft, we have, if you recall, we had like a read parquet, right? That was the source of the data frame.
Mm-hmm.
But there's no reason why you can't have a source that's more like, watch bucket, for example. And then every time a new object comes in, it just is a new row in the data frame, right? So then your data frame becomes more of an unbounded kind of data frame where you can, instead of writing to parquet, you can say write, like streaming write essentially to a bucket as well. And that way, now you can have like new JSONs dropping in, new JSONs coming out, right? And then you can kind of use your data frame that way.
Yeah, I mean, if you subscribe to a RabbitMQ, then you're essentially just a pipeline streaming service.
Yes, exactly. And so, I mean, data frames are really interesting because people think of them as this like batch compute thing, but under the hood, a lot of them are streaming. And so Daft also does a lot of these streaming operations under the hood. And so there's actually no reason why you can't express a streaming computation in the data frame. Some things don't make sense. How do you sort over a stream, right? And it's like, it's kind of hard, but you can actually do really interesting things with defining windows where then you can define more batch-based operations.
Yeah. And so I was interested about the expression kind of syntax and library that you had. And it seemed, if I was understanding correctly, that effectively, if there's an expression that doesn't exist, you can just create your own function or seemingly callable class and you dot apply. Are those the same? I mean, the expressions being more optimized, are they the same kind of thing?
Yeah, so great question. We are actually going to start moving towards more of the UDFs and Python being more of an escape hatch. That's kind of the idea.
Right.
Like that should be really, really good at most of the common operations that you want to run, right? And so in this tutorial, we've defined a lot of the UDFs to do simple things like cropping images and all that. But we want to get Daft to a point where these are run-of-the-mill operations. They should be very Daft native. And then if there's something we don't support, then yes, write a UDF for it. And if it's common enough, file an issue for it, and we might upstream that and write it into Daft itself as a expression. Because the advantage there is that if you have an expression, we can run it in Rust, which is way more memory safe, efficient, and is faster than in Python.
Yeah, and so that kind of leads to a follow-up question I have. You were talking about how Daft is lazy. It seemed like expressions were lazy. It seemed like doing a dot apply was also lazy. But if you're chaining them on top of each other, like you took the URL, you downloaded the bytes, you took the bytes, turned it into an image, are those all lazy? So if you want to materialize the NumPy array, you are then at that moment in time downloading, converting, and cropping, and then NumPy arraying all at once.
Exactly. And so now we're peeking a little bit under the hood of that, but one of the optimizations we do is what we call operation fusing. And so if you run all these things in the sequence, we don't actually fire them off as like separate tasks. We fuse them all together and run them on one pipeline, right? Which gives you a lot of advantages. For example, if you download from a URL, explode the image, if you do that eagerly, it's a lot of data, right, per partition. But if you pipeline it, then at the end of it, you have this like 32 by 32 numpy array. And so if we pipeline it that way, then your memory utilization is a lot lower. And so Daft performs a lot of these optimizations for you that otherwise would be pretty difficult to do if you were just manually trying to build out your own system.
Right, absolutely. And so in your head, that final slide you showed, where the way that you would see ML being, an S3 bucket and the data frames, in that worldview, you would still have, you wouldn't be you wouldn't suggest creating a single data frame, for example, with the images in it. You would still suggest having the image URL in data frame and the image in S3, with the understanding that you could download it in a batch way, so you don't just have this gigantic data frame.
It depends on your use case, really, right? So there are file formats out there like Parquet, which are columnar, meaning you could store your images in a Parquet file. And that's completely reasonable, because when you run a query with Daft, you'll tell Daft, hey, I just want to count the IDs column, maybe, right? And Daft will intelligently just pull down just that column. And so you don't, even though you've stored your data with all of the images in there, by using a data frame library that knows how to do these, what's called column pruning and predicate pushdowns, it can actually very intelligently query your data at rest. The caveat there is that only certain file formats support this, such as Parquet or C and kind of the columnar file formats. But you could totally store your images inline, and it really depends on your use case. If you want it kind of very high throughput, for example, to feed like downstream training or something like that, then yes, you would want to kind of compact everything and almost like a Parquet file, like a TF record. But if you are interested in keeping them pretty lightweight for metadata operations, then yeah, you could store them as a separate URL.
That's very cool. And so how do you trade off latency and throughput with this library? So if you're building a system, you were saying that by default, it can run on a Python multi-threaded process as opposed to on top of like array cluster. If you're running this in a system where the most important thing to you is really low latencies, right? Maybe your data isn't scaling to where you need multiple clusters, for example, or even a cluster at all. It can run on disk, but it just needs the latencies to be significantly faster than Pandas. Maybe you're serving it in a REST endpoint. How do you, does Daft optimize for one thing over the other, or does it make decisions kind of in the moment depending on the query?
Yeah, so the way that I use Daft in this demo is in a purely batch setting, where the most important metric in a batch setting is throughput, right? If you are instead hosting like a REST API to do all this, you would want to introduce a bunch of essentially caching to make things work better. And so Daft supports that by, you can actually call a .collect, which will pull all the data into memory. And then instead of reading from, say, like the CSV, it then reads from this like kind of intermediate checkpoint of, hey, I'm going to read from the joined data, right? And so then every query on top of that is extremely low latency. And so that's a way you can trade it off. I would say for most of the use cases for data frames, they are built for high throughput rather than low latency scenarios. For low latency, like web application, for example, you may want to have Daft write out to something that's more suitable, like a database, a live database. That really depends on the application requirements.
Yeah, absolutely. No, that makes a lot of sense. That's very cool. I'm excited to try it. Cool. So, we have 5 minutes left. We haven't gotten any other user questions. So I'm curious on your end, what got you excited to build another data frame library, in the ecosystem?
Yeah, it was really interesting. We didn't start off as a data frame library. The main question we wanted to answer was like, hey, like if I have 1 million images, like what is the best way to run a model on top of it, right? Or if I had 1 million PDF documents, like how can I best extract data and run all these commands? And then at the end of it, I want to figure out like what I actually did, right? Like did this run well? And so the first thing we tried was we defined a library or framework that was data functions. And so that's where the name Daft actually comes from, DAFT. But the idea is that I have all these data functions and I want to run them on every file, right? Unfortunately, after we did that, we were like, okay, like now we have all the data it's like kind of sitting around as JSONs. How do we then aggregate it and figure out like, oh, did we actually do a good job of, say, model prediction, or did we actually do a good job of like extracting the data from the PDS? And it's very difficult to do that without some abstraction of a table, like a data frame. And so that's how we gradually, gravitated towards, okay, we actually do need a data frame for a lot of these operations, and a lot of the existing data frames just don't cut it. I've worked with like Spark, and like I've tried out like Dask, and all of them are like either too slow, or they are very unwieldy from Python, right? And Spark, for example, if you try to make a print statement, it doesn't even show up on your console. So it's like it's very rough. And so at the end of the day, we're like, okay, it seems like the world just needs a better data frame library, and so why not we just go build that?
Well, I, for one, am extremely excited to play with it and try it out. So I'm assuming based on that the company Eventual is using Daft inside of their system.
Exactly. Eventual is going to be providing an abstraction on top of your data, which is going to be essentially a complex data lake, right? So the way that you ask questions of complex data is you can use something like Daft. And so we abstract away a lot of the underlying ways of how you store your data. And that's something that Daft doesn't cover, right? But then on top of that storage layer, we'll have a Daft layer that makes it really easy for you to ask questions about your data, and also process it and pipe it down to downstream use cases.
Yeah, that makes sense. We got one question, but I think you had suggested that streaming was not something that existed yet. They were asking about the streaming mode of the system. That's something that's in development or being planned, right?
That's in development. We actually used to have an experimental folder where we were trying some of this out. So it does work, but we wanted to make sure that like our batch story was really, really strong first. But in the streaming case, it's actually pretty interesting, where you can hook a data frame up to a streaming source and a streaming sink, and have the data frame handle kind of the in-between computations, like, running a model, or running all this like data processing, pre-processing for your model, and all that kind of fun stuff.
Right. That makes a lot of sense. Awesome. Perfect timing. Jay, thanks so much for coming on. Thanks for everybody for watching and listening, asking questions.